this is impossible. Well, what do? They work around it. They say, no, it isn't. And that's what happened with imaginary numbers. So we have this wonderful incontinuity that you probably learned about when you were younger. And they simply said, you can't find the square root of a negative number. That's a lie. You can. And you guys, I'm sure, have all heard about imaginary numbers. All they said was, well, let's just go here. All we'll do, these wonderful mathematicians, is we're going to take negative 1, we're going to get the square root of negative 1, and we're going to set it equal to I. They thumbed their nose at logic, and they made imaginary numbers, which, even in the name, are imaginary. That being said, imaginary numbers have a lot of great uses in the real world you guys are going to be able to unlock once you fully understand them. So, the basic heart of imaginary numbers is this equation. The square root of negative 1 equals I. And this allows you to solve for basically any number where it's negative. So now, if I have negative 9, well, what does that equal? If it's the square root of negative 9, I go, that's going to equal the square root of negative 1 times the square root of 9. And now all that equals, square root of negative 1 equals I. And the square root of 9 equals 3. You have 3I. Boom! I just solved it, and they told me it wasn't possible. Go back to your 6th grade teacher and be like, remember when you told me that you can't square root a negative number? Thumb your nose, they'll be like, no, you lied. You're a liar, Mr. Bangkok. Tough luck. So, that being said, here we are, and we're going to talk about kind of the theory behind imaginary numbers. Normal numbers proceed along a number line. Whoa! So we got this wonderful number line here. You got a 0 in the middle, you go 1, 2, 3, and you could go negative 2 if you want to be fancy. Negative 1, negative 2, negative 3. That's what a normal number does, real numbers. Your set of real numbers. Remember, real numbers, got that funky R with the second line. That's what you've got going along here. But then you've also got these imaginary numbers, and the imaginary numbers go up and down, sort of. Because, I say sort of, because they don't actually. Imaginary numbers with the I deals in the realm of rotation versus the realm of linear movement. And so you have a ton of useful uses. 1, 2, 3, 4, 5, and each of these are going to be I. You have a ton of useful uses for these when it comes to navigation. Because, say, you're in a ship and you're saying, we're going to be at a heading of 80 degrees. And for navigation, 80 degrees is going to be 10 degrees north of east. And when you're talking about 80 degrees on a compass, whoop, you got your compass here, you got your north, east, south, west, you're heading this direction. Well, because you have I, you can use that to then put that into a solid heading, which would be a Cartesian heading. And we're going to talk about how to do that in a second as an example for how you can use these wonderful numbers. But first you have to understand the idea of the Cartesian form for imaginary numbers. So the most basic form you'll see for an imaginary number is going to be this idea, and this is going to be your regular, traditional, run-of-the-mill imaginary number. It's going to be something, term A, and that's going to be how far along it is in the real realm. So you say maybe negative 3. Boom. And then you have an imaginary part. And we'll say it's going to be 3I, or negative 3I. It's going to be negative or positive in the imaginary realm again. And so say plus I times your B, which would be your amount, your coefficient, and you're multiplying that I term by. IB. Yes, it all connects. Proof that IB is imaginary and you're really just living a dream. Or a nightmare. Nobody knows. So, that being said, you've got this wonderful two-part term. And when you're looking at it, you say, okay, what can I do with this? You can do a lot with it, actually. The first thing we'll do, before we come back here and we talk about how you can use the rotational properties of I, is going to be, you can find its conjugate. So, we're going to go back to like a long time ago, and I'm going to erase the bottom part of this graph real quick. when you learned that any number in the form of a plus b times a minus b will end up equaling the a squared minus b squared. A squared minus b squared. Boom. You learned that. So now when you look at this, you see a plus b, a plus ib. What can I do with that? I'll tell you what you can do with that. You can use that to make that whole equation real. Now, there's a number of occasions when you might want to make it real. For example, just like with roots, you don't want having a root in your denominator. So if I have a number in the form of, 2 over 3 plus 4i, I don't want that nasty complex number in my denominator. What am I going to do? I'm going to multiply it by its conjugate. So I take it and I say 3 minus 4i. Add this right here, 3 minus 4i. Multiply it on the top too. 3 minus 4i. So remember 3 minus 4i over 3 minus 4i, that's just multiplying by 1. Nothing's changed, it just looks prettier. Boom! 3 minus 4i. So 3 times 3, 9. 4i times 3, 12i. 3 times negative 4i, negative 12i. 4i times 4i. Whoa. Dude, what happens when I multiply I with I? Well, remember, the square root of negative 1, negative 1 equals I. So therefore, square both sides of this equation. You square your I, you square your square root of negative 1, the squared square root, I just equals negative 1 if you square it. So we've squared I now. 4, so you've got your 4, so that's going to be plus 16, times, because I's been squared, negative 1. Boom! So now, that's going to be in your denominator. You drop this in your numerator, come over here, and we're going to see 6 minus 8i over, now we have 12i minus 12i, you get rid of both of those, 9 plus 16 times negative 1, 9 minus 16, and that's simply going to equal 9 minus 16 will be, 1 second, computing, 7, negative 7, over negative 7, there you go. And that's how you take your imaginary number out of a denominator. You just find the conjugate for this is just a minus, and then that makes it a real number. Okay, now I'm going to give you the fun stuff that I promised, which is how to use the rotational properties of I. When you're looking at I, the basic idea is that multiplying I by itself, what does it end up getting you? Well, the first time you multiply it, you're going to have I to 1 power will give you I. I to the 0 power, if we go backwards a little bit though, what's that going to give you? What does anything to the 0 power equal? Remember we learned it, 1. So when you're at I to the 0 power, you're going to be along this part of your graph. It's going to be the real positive side of your graph. Go up to I to the 1. It's just going to be I. So now you're going to be up on what would be the positive part of the y-axis of your I Cartesian plane. Then you go along. I to the 2. I to the 2, I squared. I squared, well remember again, the square root of I equals negative 1, so I squared just equals negative 1. Negative 1, whoa, you're back over here now. So now you're on the negative part of the real number line. You can go on, I to the 3rd, now you're at negative I because it's I squared times I, negative 1 times a single I, and now you're going to be at the negative part of the I number line right down here. And finally, if you go all the way back to I to the 4th, where do you end up? Well, you're going to be right back over here in the real numbers because, again, if you say we have I here, I equals the square root of negative 1. Remember what I told you that was important? There's a reason why I keep talking about it. It's because it's really important. Take the square root of negative 1, you go to the 4th. You take I, you go to the 4th, so that's going to be I to the 4th come down here, I to the fourth equals, well, first start by taking the square root away. So now it's going to be negative 1 squared. Negative 1 squared equals 1. And I to the fourth equals 1. What does that mean? You're back to the real numbers. So I is capable of rotating a number around this number line. So is there another way we can express a term in I? Of course there is. Remember I talked about compasses and navigation? Well, that's using an angle. Say, a sailor might say, okay, we need to go 9 kilometers at 80 degrees. If you're going 9 kilometers at 80 degrees, 9 kilometers and 80 degrees is going to be 80 right here, degrees, and you're going 9 kilometers off in this direction. So all that means is that it's just going to be a different form. And you can convert that back into traditional complex numbers. This, for when you're looking at it, 9 kilometers is going to be called the modulus. So your line is going to be your modulus, and the angle between that line and wherever your angle is going to be between, which is going to be your real axis, is going to be this angle right here. Whoop. That'll be your argument. Now, remember, you might have been a little confused because I mentioned how, oh look, it's 80 degrees. That's just because when you're sailing, measurements are off of north, which is 80 degrees from north, will bring you down. But in this case, for this complex number, it would be 9 kilometers, or just 9. 9 being your A, or not being your A, 9 is going to be your modulus, so 9 will be your M, plus that angle, which will be 10 degrees from your real axis, which plus 10 degrees, plus your A degrees. Your modulus plus your argument in degrees. So now you have this, and you're saying, okay, but the sailor's looking at a map now. And he says, I want to know what will happen, where I'm going to end up if I go 9 kilometers at 10 degrees. So he needs to know how far east he's going to end up going, how far in this direction along his real axis, and how far north, which would be along the imaginary axis, to easier look at it along a graph. Very simple to convert. So, all we're going to do, we go back, we're going to just draw it as a graph. So we say, we're going, and we're going to take a new number here, we're only going to be going at an angle of 30 degrees, which, let's go 60 degrees now since it looks like 60 degrees. So we're going to be going along at an angle of 60 degrees. 60. And we're going to be going a distance of 3. Distance of 3 at an angle of 60 degrees. So how are we going to find what our x term, or that would be then in a real and imaginary sense, that's going to be your a term, and our b terms would be? What is our bi going to be here? So what you have to do is you have to go back and you have to do a little bit of trigonometry. But don't worry, it's simple right angle trigonometry because this right here is going to be a right angle. So now you're going to look at it and say, okay, we've got a 3 here. We have 3, we know the angle here. So what do we need to find out? You want to find out what this distance is right here and this distance is right here. You have your hypotenuse, which is going to be a 3. So hypotenuse, but you need to find out what your adjacent side and your opposite sides are going to be. So to find your opposite side, you simply are going to use the sine. So that'll be the sine of the angle, sine of 60 degrees, will equal the opposite over the hypotenuse, or b over 3. And then you just go over here, 3 sine of 60 degrees. Pretty simple. Do the same thing with every side except for with cosine, because it's the adjacent side instead of the opposite side. And it would be 3 cosine of 60 degrees to find your a term. So this will equal your b term, and this will equal your a term. Now, for a generalized formula for that, you've already seen how to do it most of the time. So if you have a number in the form of your modulus plus your argument in degrees, all you have to do is go and you say the modulus times the sine of the argument in degrees will equal b, and the modulus times the cosine of your argument in degrees again will equal a. Just that simple. Converting back, you just have to do the opposite thing, which is going to mean you have, say, we'll take two new numbers for this example. Whoop. Here we go. For your imaginary axis and your real axis. Now here we have the point. You're going to be going along your real side, 4. So 4 plus up your imaginary side, 5, which will be 5i. 4 plus 5i, all we have to do, again, you take it and you make it like a triangle. So we're saying, here we're going, we need to find what our argument is, we have to find what our modulus is. Our m and our a in degrees. And then you come down here, boom, square it off. So your height here, that's going to be your 5i, how far you're traveling along the imaginary axis, and your 4 will be your real axis distance. It's really simple to find the modulus. That's just the good old a squared plus b squared equals c squared. Pythagoras. Now, do you have that a squared plus b squared equals c squared? 4 squared plus 5 squared will equal that squared, which just means square root 4 squared plus 5 squared. If you'd like to get out your calculators and do it, feel free. It's going to end up equaling a not so pretty number, so I won't do it up here, but you get the idea. Now, it's a little bit more complicated to find out what your angle is going to equal, or your argument, What your argument is going to equal, now that's going to be going to the final one. We already talked about sine, we already talked about cosine, now we're going to be talking about tangent. Because again, you have your opposite side and your adjacent side. And opposite over adjacent, that's going to equal the tangent. So the tangent of the angle, or the tangent of your argument in degrees will equal 5, because that's your opposite, over 4. Now all I have to do is take the inverse of the tangent, or as you might see on a calculator, tan negative 1 of 5 over 4, and that'll equal your angle, or your argument. So that's how you get your argument, and remember, to get your modulus, it's just going to be the a plus b of your form, so a squared plus b squared, and then the square root of that, because that's going to equal c squared, boom, and that'll equal the modulus. And I do believe that about covers it. We are going to have to go over a little bit of algebra, though, before we're done with imaginary numbers. And this is about as straightforward as it gets. First things first, sums of imaginary numbers. What happens when you add imaginary numbers, say 4 plus 5i, and you're going to be taking that, plus negative 3 plus 6i. It's really straightforward. All you do is just you add like terms. 4 plus negative 3, that's simply going to equal 4 minus 3, 1, 5i plus 6i, plus 11i. Done. That's sums. Multiplication, if you say instead of adding these, you're multiplying them, you're simply going to treat it like the I is an X for the moment. Treat it like standard variable and use FOIL if you'd like to use FOIL, or just multiply it out normally. So if we're saying we're to FOIL it, first that's going to be negative 12, and then outer 4 times 6i plus 24i, inner, go to your inside here, 5i times negative 3, negative 15i, and finally last, 5i times 6i, and you're going to end up getting plus 30i squared. And now all you have to do, just to make this tidied up a little bit, get your inside two terms added together. And remember, I squared equals -1. So instead of it being 30i squared, it's going to be -30. So now all you have is -42, because you add the -12 and -30. And then you add these together, you've got your +24 and -15, which will just give you +9i. And there you go, you have it in your standard form. And to divide, again, it's the same kind of deal. Just follow the standard rules for dealing with binomials, and then once you're done, check for any I squareds or I cubes or any I to an exponent so that you can then simplify a little bit. Nice going, and remember, because IB is imaginary, this has all been a dream.